everyone who uses Ethereum or a settlement layer, or for that matter, a data layer, essentially is paying some sort of rent to this service provider. But the fact remains that people don't want to pay rent to landlords. They want to become their own landlords, and they want value to accrue to their own token.
You're now plugged into the Delphi podcast.
Hey everyone, welcome to a very special episode of the Delphi podcast. My name is Jon Charbonneau. I'm a research associate over here at Delphi, and I'll be your host for today. But you're not here to see me. You're here to see our two awesome guests I'm super excited to have on today. We're going to be talking Ethereum, Celestia, and everything modular. Fair warning, some of the stuff that we talk about today is going to go pretty deep. So we finally brought together two of the best guys possible to teach us. We've got Dankrad Feist here from Ethereum and John Adler here from Celestia. I imagine you two need no introduction from most of our audience, but if you want to go ahead and please give a brief intro before we get started. Dankrad, if you can go first, please.
So yeah, thank you for having me. I'm Dankrad. I'm a researcher at the Ethereum Foundation. I've been doing research on Ethereum since early 2019, and I've been working on different topics in the direction of sharding, the proof custody, proof stake, and so on. Yeah. All kinds of things that we need for the future upgrades of Ethereum.
I'm John. I'm one of the co-founders of Celestia Labs, Chief Research Officer. So I do protocol research and specification work. And generally for the past several years, I've been involved in layer 2 and general blockchain scalability, both on Ethereum and on other chains such as Celestia and Cosmos and so on.
Awesome. Thank you. So I'm going to go right back to you, John, for the first question. You can hit on it before Dankrad responds, and then we'll see how things roll from there. Just as a background for everyone and a reminder, Ethereum and Celestia have, of course, been the two biggest names banging on the table lately, the importance of building secure base layers to host rollups on top of them as a route to scaling. So a couple of these things that rollups will need are a place to post a ton of data to give them data availability guarantees, and they need to settle somewhere. So for example, posting proofs, a place to arbitrate disputes. So something to note is that Ethereum offers data availability and settlement in addition to a general execution environment, while Celestia chooses only to offer data availability and consensus over that ordering. So then looking at what some of the different stacks can look like broadly, if you look at today's standard Ethereum rollups, they can rely on the base layer for both of those roles that I described. Though noting the next couple options I describe are also possible on Ethereum, and you could even do things like enshrined rollups down the road. So next, there are recursive rollups. So basically pulling that settlement part out of the base layer, and you could stick it on, say, an L2 settlement rollup, and then an L3 can sit on top of that. And you can also have sovereign rollups, where there's no separate settlement layer used. The rollups can just settle proofs client side. So starting with John, if you could please break down in a bit more detail, what exactly are these data availability and settlement things? Why are they so important? And how should we be thinking of these things in the context of potentially building these different stacks I described and the various benefits and trade-offs and designing these different stacks too?
Sure. So fundamentally, data availability, or DA, as you may see it shortened on Twitter and whatnot, is the ability to verify that some data has been published to the world. The reason this is important is that if you don't know that data has been published globally, then you could end up in a situation where data is withheld. And if data is withheld, then you can either, in the case of fraud proofs or a system without ZK or validity proofs, you can end up in a situation where someone can include an invalid transaction on chain and no one can really prove that this happened. And if you are using a system with validity proofs, then someone can advance the state of the chain to a state that no one actually knows what that is, except, of course, the person who advanced it, therefore effectively rendering the chain useless for everyone else. So data availability is a pretty important feature. Now, why was this not brought up as an issue back in the day of Bitcoin and Ethereum when it started, more than 2 years ago or 3 years ago? No one talked about DA, really. I guess Vitalik talked about it a bit in the context of sharding, but it wasn't in the common conscious, especially not among Bitcoiners, that DA was even a problem. Why is this? Is that the classical blockchain security model relied on everyone running a full node, And if everyone runs a full node, well, one of the things a full node does is it fully downloads every block. Therefore, it implicitly verifies that the data behind that block is available. This, of course, is fundamentally not a scalable model of everyone having to run a full node, because it means that if you want to be inclusive to as many people as possible, you are now limiting your system to what is the computational capacity someone can provide, the lowest common denominator, or maybe Raspberry Pi or something. You fundamentally can't increase the transactions per second of your blockchain very much. So this is where the notion of trust minimized light clients come in. And sharding, when it was originally proposed, is essentially trust minimized light clients. You have a trust minimized light client for every other shard. And one of the properties that trust minimized light clients have is that rather than fully downloading blocks, well, you only download block headers, and then you either have a fraud or validity proof on the actual state transition of the block. But now suddenly you're not fully downloading the block, and a validity proof or a fraud proof can't tell you whether or not the data has been published or not. This is because data withholding is not a uniquely attributable fault. So if someone withholds data, then either they could be withholding the data and then someone warns about it, or whoever warns about data being withheld is lying, but a third party has no way of actually knowing which one of those two cases is reality. So you end up with a situation where now, with this new modern security model for blockchains of having trust minimized light clients everywhere, not just in sharding context, but also in this modular context, we need a solution for data availability. And presumably we'll talk about this further in the podcast about there's various ways to do this. But this is why it's so important, is because we're moving away from the notion of everyone running a full node to this new world where 99% of the users can run a trust minimized light client and have very, very strong security guarantees while doing a very small amount of work. The rest of your question was around settlement. So this one's a bit tricky. Some people define it slightly differently. I guess I would define it as a place where proofs are verified. So this could be either validity proofs or fraud proofs for your trust minimized light clients, and I guess full nodes too. And there are various places settlement can happen. In a normal blockchain, like a classical blockchain, like Ethereum, for example, the blockchain itself essentially is its own settlement layer, that users running full nodes can verify the validity of Ethereum blocks by just verifying them, right? They just execute the block, and they're their own settlement layer, essentially. So the settlement layer for a normal blockchain is layer 0, the social layer, right? Everyone runs a full node, and they can verify that the blocks are valid. But in the context of rollups, for example, then you can have the blockchain rather than the people running the full nodes, but the blockchain virtual machine can serve as a settlement layer and verify proofs that the rollup is valid or invalid. So in that case, the settlement layer, in the case of a rollup on Ethereum, the settlement layer would be Ethereum, and after that, execution happens within the rollup itself.
I mean, it's clearly an excellent introduction into why data availability is important. So I think I have nothing very much to comment on that. I think one of the things that have been raised in the past about the differences between Ethereum, what Ethereum is building, and what Celestia is currently building, is the integrated settlement layer, which clearly is, for one reason, clearly true for historical reasons, because Ethereum already has it, so there's no reason and also really no way to get rid of it. But also, I think it may be important to emphasize why I think it is an advantage to have this. And the number one advantage I see is basically reducing fragmentation. So basically what I think is a bit more of a nightmare of a world is n-squared bridges between all kinds of different systems to maintain versus just n bridges to one settlement layer. So I think that is one major advantage we have with this default settlement layer that we have integrated into Ethereum. And I think the other big question, I think that maybe I would ask John to comment on, I would be interested in, So one of the concerns that I would have without having a smart contract system in the data availability layer integrated is that it basically means that you can't really bridge the native asset of the data availability layer into the rollups. And so I think that's a severe restriction, because in my opinion, block space is like the first really valuable commodity we have in the decentralized space, and like not being able to use an asset that is secured by that, for example, in DeFi, in order to borrow against it, in order to create stable coins and all kinds of other construction, basically using it as collateral is a severe downside of not having a settlement layer integrated into the protocol.
Yeah. So to give some additional context to readers who aren't familiar with Dankrad brings up a very good point, which is that the way rollups work in Ethereum today is that you can move assets from Ethereum to the rollup through a trust minimized two-way bridge, because the rollup implicitly fully validate Ethereum, and Ethereum has like the rollup contract on Ethereum will effectively be a trust minimized like client to the rollup. So now you have trust minimized on both sides. You can build a bridge both to and from the rollup. Celestia doesn't support this because the Celestia chain itself does not have smart contract execution. So you can have a trust minimized one-way bridge from Celestia to the rollup, but you cannot have a bridge backwards. This is a limitation of the model. It comes with certain upsides in the sense that not having settlement at the base layer means that the base layer doesn't have to do the extra work. But it does bring some additional challenges, such as the fact that you can't have a trust minimized two-way bridge. I don't really see this. This is more like of an opinion thing, because as it turns out, most of the stuff in the blockchain is opinion things. It turns out, and less about technical stuff. But the opinion thing is, for example, WBTC, WrapBTC is heavily used in Ethereum. There was recently a bridge that opened on Avalanche for wrapped Bitcoin, and then in one day, there are more wrapped Bitcoin on Avalanche than the Liquid network on Bitcoin had over the course of its entire lifetime. So many people will use bridges that aren't trust minimized, such as wrap Bitcoin. Many people, even in rollups today, will use protocols that aren't completely trust minimized to move their assets to and from. So I don't see that there's a very hard need that you must have a trust minimized bridge with a native asset, because you can always have things like tokenized representations of the asset. You could have something like a stablecoin pegged to the asset, and you can have trusted bridges, like, for instance, maybe a wrap Celestia token, to be used both not only on rollups on Celestia, but potentially even on other chains, such as Ethereum or Osmosis for Cosmos or the Cosmos Hub or what have you.
Right. I mean, I fully agree that these will be built. Like, of course, we will have these bridges, but I'm very critical in general of multi-sigs, for example, as bridges, which, for example, all the Bitcoin bridges you mentioned are in practice. And like, I think that's a very severe restriction and not sustainable in the long term. So I see like one of the big advantages of building these data availability layers, that we can move away from that and build better bridges. And so it just seems to me that, at least for now, like, I don't know, maybe in the future Celestia will change its design. That's kind of like unfortunate to throw that away.
Yeah, but like I mentioned, I expect that a stable coin that is pegged to the Celestia token's value should emerge to fill in this gap. So it wouldn't be a bridged or a wrapped asset. It would just be a stable coin, essentially, just like how DAI is.
Right. But that doesn't solve the collateral issue. Like, basically, that stable coin would have to be collateralized with something else. So you can definitely do that, but it has its downside. It means you limit the use of your native asset as collateral.
Yeah, that is the trade-off.
A question somewhat related to this. So one of the reasons that you would want to be able to easily use the native asset, kind of the point you're getting to, as collateral, having a useful asset helps give that asset economic security. And also a part of having economic security could potentially be having everything in one base layer. So for example, with Ethereum, like you would have data availability, settlement, and just general execution, all of those fees kind of going to one asset. And I would be curious to get both of your thoughts on how important is that aspect of having a base asset that has built up and is able to build up all this economic security, as opposed to potentially pulling that apart into different components.
I personally wouldn't say that use as a collateral gives an asset economic security. Like that doesn't that doesn't make the asset valuable. It needs to derive its security from some other means, basically some other means of generating yield. And so I see for now only two of these, which are the settlement layer and the data availability layer. And I think like short term, we will probably see that that the settlement layer still generates much more value. Like we've seen that already, that we have had significant fees on Ethereum in the past, and also some on other settlement layers. But long term, I believe that the most valuable asset will just be the data availability. That the block space will become the most valuable asset in the decentralized economy, and so like that's why I would say like it's very important that we can use this asset as a collateral.
Sure. I'm maybe not going to answer the question directly, but I can kind of discuss my thoughts on something tangentially related, which is that in light of the recent, at the time of recording, news that DYDX will be no longer pursuing a path of being a ZK rollup for its V4 deployment, but it will instead be building as a sovereign Cosmos zone. There was discussion around this topic on Twitter and so on. The kind of notion that everyone who uses Ethereum or a settlement layer, or for that matter a data layer, essentially is paying some sort of rent to this service provider. Now, obviously, from the perspective of the landlord, they want everyone to use them and pay rent to them. And obviously, from the perspective of the renter, they want to become their own landlord so they can do the same. So DYDX could pay rent to Ethereum or to another chain, or it could become its own sovereign chain and have its users pay rent to its own token and accrue value to its own token. We've seen this happen to a few other projects as well. Compound, I think, was one of them who wanted to build their own chain. They ended up coming back to Ethereum, but that just because they happened to be unsuccessful doesn't necessarily mean that all future projects will be unsuccessful, because they could have been unsuccessful for technical reasons. But the fact remains that people don't want to pay rent to landlords. They want to become their own landlords, and they want value to accrue to their own token. So I expect that, or you kind of have this weird, like stuck between a rock and a hard place, because you want your base layer to have as much value accrual as possible. You want it to collect as much rent as possible, because then value accrues to that particular token. But the applications and the protocols that build on top of this don't want to pay all that rent. They want to pay as little rent as possible, and potentially they want to pay rent to themselves. They want users to pay all the rent to their token. So you want the base layer to accrue as much value as possible, to be as secure as possible. On the other hand, applications don't want to do this, because applications are selfish, and to a certain extent they should be. So you're stuck between this rock and a hard place. And it's not necessarily clear at this stage where on that line we'll end up. If anything, potentially we'll have multiple solutions at different points on the line. For example, Ethereum is very much on the scale of it wants to accrue all value of everything that runs on top of Ethereum to the Ether coin. Celestia is value that accrues in the form of MEV, in the form of constrained execution layer block space, does not accrue to the Celestia token. The only thing that accrues to the Celestia token is space on the data layer, constrained space on the data layer. So it seems like it doesn't have as much value accrual. However, it also means it won't have apps leaving because it's trying to extract too much rent. So you kind of have this weird situation. I'm not sure which one of these approaches, or even if either of these two approaches is going to be the winner in the long term. But just noting that there's a kind of a gradient scale here along how much rent the base protocol extracts versus if it extracts too much, then it pushes protocols on top of it away.
So I think I would push back a little bit into that Ethereum tries to extract as much rent as possible. I don't think that is how we're designing the protocol, and I think that is not the goal. The goal is to have a sustainable protocol. And as I said, so I believe that the most valuable asset that we're creating is this block space, and by which I mean for the future the data availability space. And so what I think is that why I don't think that a decision like DYDX is likely to be long-term sustainable is that they now have to fully pay for their own security out of their own token. And in a scalable world, that should be much, much cheaper if you pay instead a scalable blockchain for it.
So this is why I counter retort, which is that security does not require settlement. It doesn't require some sort of enshrined, Ethereum-like settlement layer. Security can be derived solely through data availability and ordering. So in this context, if DYDX were to not be its own Cosmos zone, where it would have to pay inflation completely for its own security, but instead purchase security from the likes of Celestia alone, that would actually be the minimum cost it would have to pay to get a certain amount of security, because they're not also paying for settlement. They're only paying for data availability and ordering.
So this is completely fair, but I also think that Ethereum can provide exactly the same. They could also choose to only pay for data availability and not use the settlement layer. I think it's a less optimal solution, but I think they could do that.
Great thoughts. One other question I had on this topic before we move on. So one of the points that you had made, Dankrad, as far as the value of having a settlement layer so we don't end up with these n-squared bridges. Another stack that we kind of didn't talk a whole lot about here is the option of you can put these things with a settlement rollup in between them. And then, for example, you could also have that a more restricted environment. So it's optimized and restricted just for posting proofs to it, token transfers, etc., which helps minimize the cost of, for example, now when I post my proofs to this thing or I settle through this thing, I'm sending tokens. I'm not competing with this really expensive general execution environment of Ethereum where all of these whales are transacting, so it's really expensive for me to do this. So I'm curious to hear both of your thoughts on if that is also an attractive strategy, if those trade-offs are worth it for potentially pulling that stack apart again.
It might be potentially good if I give a bit of background on what you're talking about to listeners who may be unfamiliar, which is that if you have a rollup today that on Ethereum that uses Ethereum for settlement, you can use Ethereum essentially as a communication channel to move arbitrary messages and funds in a trust minimized manner from one rollup to another rollup. You can use Ethereum. You can go through Ethereum essentially. You can also have direct rollup to rollup communication, but you always have the option of using the settlement layer. Now, if you have a rollup on top of a data-only layer, such as Celestia, well, you can't use Celestia to settle anything because Celestia doesn't do smart contract execution. You can't move funds around through Celestia. You could do it directly rollup to rollup, as before. But no one is stopping you from just having a rollup on top of Celestia. We're all consenting adults here. You can always put a rollup on top of your rollup and make layer 3, or you can put a rollup on top of that. So in this context, you can have a rollup that essentially serves as a settlement layer. So the rollup itself doesn't do a lot of execution, just does a small amount, just enough to verify proofs, fraud proofs or validity proofs, and pass tokens around essentially. So it's a very constrained execution environment. And then you can build your actual execution rollups on top of this. In this context, you're essentially taking what you have on Ethereum today, and then you have this data layer under it. But fundamentally, the tree of rollups, all connected to a single settlement layer, still exist in this model. So this allows you to have the same, using the settlement layer as a communication mechanism between rollups to avoid bridge fragmentation, because now you don't need a bunch of bridges, to rollup and so on, potentially with different security guarantees. You can just use the singular settlement layer for communication, for bridging. So you remove that potential n square issue. Hopefully that's enough background context for the readers. Now your question was, was your question directed to Dankrad? Should I pass it back?
No, you can keep going. Just basically, whether do you think that those trade-offs are worth it? Is this going to be an attractive thing that we see a lot of? Or do you think that more of something like sovereign rollups is kind of the end game that you expect to be more common on Celestia? Like, where does that trade-off spectrum kind of lie?
Yeah, so this also applies to Ethereum to a certain extent, because you have projects like Starkware, for instance, and Fuel Labs, who have demonstrated that the projects that they're building on are also suitable for having L3s built on top of them. You can build a rollup on top of another rollup, even on Ethereum today. So this is not something that applies exclusively to a data-only chain, is that you can always have rollups on top of a settlement layer, optionally on top of a data layer. So whether or not I expect one to be more prevalent than the other, I wouldn't say I expect anything, except expect the unexpected. The world is full of surprises, and I can't really predict which one will be used more. The only thing I do expect is people will experiment with both sovereign rollups that are directly on top of a data layer and essentially enforce their own settlement, similar to Cosmos zones as they exist today, but with shared security. And I also expect people to experiment with settlement rollups. At Celestia, we're building one called Submos as kind of a proof of concept developer thing that people can use. There's essentially a very restricted EVM that allows people to copy-paste rollups that exist on any EVM chain today, and they could just deploy to Submos, and they would just work TM. And I expect people to experiment with both approaches, because neither approach is strictly better than the other. They have trade-offs.
I think generally I'm in agreement here. I think the one thing that I am wondering about is the claimed advantage of not having to compete with whales on your settlement layer, because I feel like any sufficiently general settlement layer that is able to process all rollups can also simply be used to implement general smart contracts. So who is to stop anyone from simply doing that and start competing with the rollups at the settlement layer as well? I think that is going to happen in the long run.
There are possibilities. I'm just going to name a few off the top of my head, not claiming these are perfect, but just possibilities. Is you could have, for instance, a settlement layer that has contracts being whitelisted. So to deploy a new contract, you have to pass through some whitelist. This would be controlled essentially by the social consensus of the settlement layer itself. And this would allow the set of rollups that agree to use this common settlement layer to essentially have this guarantee that the settlement layer would work for them, and it would not be subject to someone deploying arbitrary smart contracts. And if anyone else wanted to join, they would essentially ask the current set of people that are there, hey, can I join? And then they would get inducted in or not. Obviously, this isn't perfect because you introduce some notion of permissionedness, but at the same time, who's saying that a set of rollups can't organize something amongst themselves? Well, who are we to tell them that they can't have a permissioned settlement layer amongst themselves, right? They could if they wanted to. There's other alternatives. You could, for instance, you could change the gas cost of particular instructions to make it very, very expensive to do anything that isn't like verifying a fraud proof or a simple token transfer. There's various clever things you could do along the lines of changing resource pricing to heavily discourage anything that isn't that. So there's a few alternatives there. But again, this is not like a concrete proposal. It's more like just off the top of my head, there's some options.
Makes sense. So moving on to another question that we had. So as we discussed, these base layers need to provide guarantees of data availability. And so at a very high level, what we can do is extend that initial data using erasure coding. And then clients, they do data availability sampling of that original and the parity data to check that it's available. But we also need to know a second thing, and that's whether that original data was extended properly. Because otherwise, knowing that improperly extended data doesn't really help us in this scenario. So there's a couple options here, and you guys are taking slightly different approaches to it. One of them involves using fraud proofs, which will be in Celestia's design, and Ethereum's design will be using KZG commitments. So it may seem like a very nuanced specific point, but it does have meaningful effects on some broader design choices here. So Dankrad, we'll start with you for this one. If you could give us an explanation of how these fraud proofs and KZG schemes would work, and what are the different implications of them?
Sure, yeah. So to quickly summarize maybe, so the way data availability sampling works is you have your original data, and what you do is you encode it, John already mentioned it, into an erasure code, which is basically a longer version of the data with a redundancy property, with the property that any fraction, so a certain fraction of the data, say 50% of this erasure coded data, can be used to reconstruct the full data. And this is required for data availability sampling because what you want is you only want to download a small constant number of samples per block, because otherwise it doesn't scale. If you had to download 90% of the samples per block, then you didn't save much. So we want something like a few tens of samples per block. And due to the erasure code, we know that this is enough because you can, with a small number of samples, you can ensure that, say, 50% of all the samples are available. And now the problem that John alluded to is the next problem is, but how do we ensure that this erasure code is correct? And essentially, there are two different approaches. There's either the approach that was first proposed in 2018 in the paper by Mustafa and Vitalik and one other person, which is about introducing a fraud proof mechanism. And the idea is this, that, so a naive fraud proof doesn't work because if you simply have to send all the data in order to prove that there was fraud, then you haven't really saved anything, right? Then you might have average case savings, but you don't have worst case savings. So we need a fraud-proof mechanism that sort of scales as well. And the way it was suggested was to encode data into a two-dimensional object, and so that every row and every column can individually serve as a fraud proof. And so the fraud proof is only root n of the data size. So we have a significant saving there as well. And what we found is as the big disadvantage of this approach is that we want to have clearly validators voting at every block for what is the correct chain. But how do you vote if you're waiting for a fraud proof? Like, how do you vote if you don't know yet whether the coding was correct? Well, you could wait long enough so that you're sure that fraud proofs have arrived, but you would typically want to be really sure. You want to wait at least minutes or ideally hours to wait for a fraud proof so that you're not voting for an incorrect chain. So that would be like a huge downside of this sort of approach, that you would introduce a huge latency. Or the other approach is that you simply require that validators do not just sample, but they instead download all the data. And this is the approach that, as far as I understand, Celestia is taking, which is something that we're not comfortable with at Ethereum. What we want is this decentralized validator set where you can easily run a validator at home. So with the fraud-proof approach, we're basically stuck here. Like it doesn't quite work for what we want to do. So instead, what we need is a validity proof for the erasure coding. Like we need a proof that, like zero-knowledge proof that shows you immediately that the coding was done correctly, and you don't need to wait for any kind of fraud proof. Yes, so the naive way would be to take a Merkle root of an erasure code and simply construct a complete validity proof for it. But that's not currently practical. That would be a huge amount of computation that needs to be done. Maybe at data center scale, you could do it in seconds, but definitely not on like normal machines or GPUs. But what we found out about 2 years ago, that with KZG commitments, which is a type of polynomial commitment, you can actually compute these proofs relatively quickly, and it actually becomes plausible for relatively not too large sized machine to compute these proofs, and it's very easy to verify all of them. So this is the approach we're taking at Ethereum in order to enable this very decentralized validator set where you can still validate at home that we simply encode the data using these or we commit to the data using KZG commitments, and that means that you do not need to wait for any kind of fraud proof, and you immediately know that the data is encoded correctly.
So with respect to the fraud proofs / validity proofs, Dankrad made a very good explanation, right? There's some trade-offs here, right? Fraud proofs might introduce higher latency in some cases, but are much cheaper. Validity proofs will be much more expensive, so there's various care you have to take there to make sure that this expensive stuff isn't on a path that someone has to pay for it, but have lower latency in some cases. I'm not 100% convinced that using validity proofs is kind of the be-all, end-all solution. I've generally seen it, validity proofs in general, being suggested for many things, not just here data, the validity of erasure coding, and generally it turns out that they have various limitations, computational overhead is non-trivial, and so on. In the specific context of data availability, one thing I'm not convinced about is the fact that they can completely remove the need for waiting. Because one step that needs to be done in during the data availability sampling process isn't just sampling, but it's reconstruction of blocks. This is why the current proposal for Ethereum erasure coding uses a two-dimensional square, because in the worst case, you don't want to have to reconstruct the entire, you don't want full nodes, users running validators to have to reconstruct the entire block, because, then you're back to where you started. You'd like them to reconstruct a single row or a single column, and this is not the reason that fraud proofs use a two-dimensional square is so that fraud proofs can be a single row or column, but the same actually applies for reconstruction of the block. At Celestia, we have a notion of partial nodes, which don't really exist on other blockchains. A lot of blockchains might have light nodes as full nodes. Celestia has a notion of partial nodes, which do exactly this. Rather than fully downloading a block, they can download either a subset of all blocks, or they can download subsets within a block. And that's because rows and columns have their erasure coding computed independently of other rows and columns. So the last step of the kind of data availability sampling process is you still need to have a step where full nodes attempt to reconstruct the block to ensure that it can be reconstructed by the network. Because if everyone just has a bunch of samples flying around, but no one can actually reconstruct the entire block, then the data isn't actually available to the network. And this always requires synchronous communication, because you always need some node to be able to collect samples from a bunch of other nodes, reconstruct it, fill in any proofs or erasure coding for any samples that weren't any shares that weren't distributed to the network but are recoverable through erasure coding, and then finally make this available to the rest of the network. And this always requires synchronous communication, but it's in a way that's subtle and not obvious to analyze. And I'm not convinced that using validity proofs means that you can just ignore this synchronous communication assumption and say, yes, I can sign off on a block as soon as I've sampled 10 samples, but I'm not sure if the network can actually reconstruct it. I guess we'll find out. I'm sure there's going to be rigorous analysis on this, so I'm looking forward to it. I'm also glad that the Ethereum team has chosen to use a two-dimensional square to avoid this exact case, validator nodes having to download the entire block to reconstruct it. I know some other projects that are working on the data availability landscape don't do exactly this, and that do have linear cost worst case operations. They shall not be named. So at least E2 is doing a good job in this regard.
Unfortunately, it's actually worse. It's n log squared n, I think, the worst case cost. So that's what makes it unattractive. I didn't understand your concern here, because you said that if once you've done your samples, you don't know if you can vote for it because you don't know if the network is going to reconstruct this. However, the assumption is that your samples ensure that the network can reconstruct it, at least if it's enough validators that can see this.
The network can reconstruct it under a synchronous communication assumption, which is the same assumption of a fraud proof. So it depends. It depends what your assumption is, right? Like let's say you assume that it's a few hours. Then in the worst case, you could find out that a few hours later you can't actually reconstruct the block because the communication latency, for whatever reason, was higher than an hour.
First, that's a very different assumption. The problem with the fraud proof is if you vote every 6 minutes, say, for example, which would already be very slow block time, you would have to be sure that the fraud proof will be constructed in 6 minutes. Whereas here, there's no such constraint, right? After you vote, it is okay if it, say, took 1 hour to reconstruct, which is very unreasonable, I think, to think that it will take that long. But anyway, I think it's a very different type of constraint.
If I could interject, it's basically, is there a case where if, assuming the cryptographic assumptions aren't broken and the validity proof is fine, there's no bugs in there. Okay. Is there a case where the validity proof is valid, people vote on it, yet the block later on cannot be reconstructed by someone? That I run a full node and I cannot actually reconstruct the block.
I would argue that cannot happen.
But if for instance, there was too high latency of communication, it could be that you can't reconstruct the block within some bound, and if the communication latency is too high, maybe you can't reconstruct the block at all.
Right. So I think that's an arbitrary, for any synchrony assumption, the difference is, let's say we do make a 1 hour synchrony assumption, then in the which I think 1 hour is a fairly reasonable assumption to make. Then in the fraud proof world, the problem would be you can only vote for one block if you don't want supernodes. You can only vote for one block every hour. Versus with the reconstruction one, I can keep building the chain, and then reconstruction might take an hour, but it will be done. And it's fine because I know that it will be done. So with a very loose synchrony assumption, I still get the reconstruction, but I cannot do the same for the fraud proof for voting.
Perhaps that's the case, but I would definitely like to see kind of more conclusive analysis on this particular case.
Awesome. Moving on to our next question, as we kind of alluded to before, one of the points that this KZG versus fraud proof kind of debate leads into, it relates to the consensus mechanisms that Ethereum and Celestia are both using. So for background, Celestia is going with the battle-tested Tendermint here. One of the potential downsides that people would see from that is that it has a relatively limited validator set compared to something else like Gasper, which Ethereum has built from the ground up, and they've been testing on the Beacon chain, and will fully transition to after the merge, which does allow for a much larger validator set. So the question then becomes, when you're looking at these different consensus mechanisms, how important is that you are able to allow hundreds of thousands of different validators to participate actively in consensus? Especially, is it likely that a handful of large players are just going to dominate the majority stake anyway? And doesn't social consensus guarantee censorship resistance anyway, where if validators are censoring, we can just fork them out? While it sounds like a nice thing to have, is it in reality that important to be able to have hundreds of thousands of validators? I'll turn it to Dankrad for you to kick it off here.
Yeah, thanks. So yes, I believe that supporting a large number of validators is important, and I think, clearly we can see that there are certain forces of stake centralization, and we are watching this, and there's a limited amount of things that a protocol can do about this in the end. But what I believe in. So as you have mentioned, it's very important that we can fork out, say, censors if censorship happens. What I think, so I think this is true, and this might be construed as an argument that it doesn't matter, like 100 validators is enough, because like we could just keep kicking out the censors until we end up with a validator set that we're happy with. The one problem I see with this, or rather two problems I see with this, is that if you completely remove the ability to run at-home validators, then you don't have certain fallback mechanisms. So Ethereum can very credibly claim to be able to run completely using at-home nodes. It doesn't need any support from data centers or anything like that. And that means that, for example, certain regulatory targets are not available. You cannot just like try to regulate the stakers, for example, which is a possible target if you have a more limited validator set. And the second thing I would say is it also is a way to avoid plutocracies. So basically, the way that that basically the more centralized validators could also not even being forced to anything, but just by way of the way they operate, or by how rich in the native asset they are, have certain opinions on certain transactions that should be censored, for example, and that can have the same effect as censorship, and that might also be hard to remedy if you don't have any ability to run the network in a more decentralized manner.
John, do you want to give your thoughts?
Sure. I mean, philosophically, there's more similarities than differences between Celestia and Ethereum. So, especially when you compare it to the traditional finance ecosystem. And the differences are very subtle. What Celestia was kind of designed for was not maximizing the number of consensus participating nodes. It was specifically optimizing for minimizing the worst case cost of atomic cost that someone needs to bear in order to contribute security to the network and hold the block producers accountable. So to explain what that means, it means that there are certain actions that people may need to take to hold the validators accountable. For example, if the validators produce an invalid block, well, you may have a fraud proof that the block is invalid, right? And this fraud proof, maybe it contains multiple steps, some of which must be done atomically. It must be all or nothing. That if they don't do all of the step, then their work is essentially worthless. So we want to take, these atomic actions, take the one that is most expensive that someone must do, and then minimize that cost. This is a different optimization target. It ends up looking, compared to certain other systems, it does end up looking much more similar to ETH2 than not. But it's a subtly different optimization target. And the reason for this is that, and I actually discussed this at length with Anatoly on episode 0 of the No Execution podcast, which you can see on the Celestia podcast site. It doesn't really matter if the validators if they misbehave, because you can always hold them accountable, right? If users run nodes that are able to contribute security to the network, and note that I didn't say full nodes here, because we live in a world beyond just everyone runs a full node model, right? We have a world where people can build fraud proofs, people can do data availability sampling, they can do reconstructions of individual rows or columns of the erasure-coded square, and we want that each of these operations that are atomic, we want to minimize that cost so that people don't have to run full nodes to contribute security to the network. They can run partial nodes, right? They can run light nodes that do a bit more work than a regular light node. And as long as you have enough of these, and you should, if they're very cheap to run atomically, and you've minimized the worst case cost for these, then it doesn't matter if the block producers are malicious, if they try to censor, if they try to create invalid blocks, they will just be caught. They will be held accountable through social consensus. They will have their stake burned. And it's kind of funny that, this positioning that I have is essentially diametrically opposite to the position that Solana has. So it's kind of funny that, you have essentially at this stage, anyone who says this is not a good optimization target or this is not the best optimization target, they're potentially more aligned with Solana's vision than they are aligned with the vision that we have at Celestia. Now, why is this important? Why I do not need a large number of validators is because so long as you can hold them accountable, even if there's only a single validator, then you can slash them. What matters is not the number of validators, but rather the stake that the validators have in play that can be slashed. And you want to maximize that number. You want to make it maximally expensive for them to attempt to attack the system so that you will penalize them. And when you penalize them, it has a very real economic penalty. If you can't maximize that cost, then it's cheap to attack the system regardless of the number of validators. Now, to address specifically the point of at-home validators, I think this is kind of overblown because at the peak Ethereum price, it costed 100,000 after-tax US dollars. That not only did you need to have in cash on you, you also needed to lock it up for several weeks, I think, to get into the entry queue, or maybe even like under order of months to get into the entry queue to become an ETH2 validator. You'd take the 100,000 US dollars, wait in the entry queue to become an ETH2 validator, and only then could you actually start being a validator. And you have all the uncertainty around withdrawal delays. This is a very large opportunity cost. $100,000+ plus opportunity cost. I think if you have that much money, you can afford $2,000 to run a full node, and you can afford a gigabit internet connection. How much is it? $100 a month, right? I have a gigabit internet connection in Canada, which is notoriously bad internet, for like $80 a month Canadian. Which in Canadian pesos, that's like 50 US or something like that, right? So people can easily, if you can afford $100,000+ in stake, you can afford $2,000 to run a more powerful full node. And it turns out that's all you really need for global throughput. Like you can easily get 1,000x on what Bitcoin does today in terms of data availability capacity on a $2,000 full node and a gigabit internet connection. And this is really all that's being asked. We're not asking for a trillion-x throughput here, right? Like we're talking about conservative numbers, and you can actually run this at home, especially when you compare it against the cost to be a validator, just to put up the stake to be a validator.
Right. So I think we completely agree on the first part, on the being able to validate it very cheaply. I think there's not much difference between us that we want to optimize for that. I think like the part where we disagree more is that the validator set doesn't matter. So we think it still matters, and that's because it's much harder to enforce non-censorship. So that's where it becomes difficult, because you can't automatically slash validators for censoring transactions. So we need a much higher resistance, because this sort of social slashing first has to be a rare event, and second, it needs to actually have a fallback. Like if your social slashing means that you have to slash all the validators, then it doesn't work, because then you have no chain to run. And so you need a way that you will always find some subset of validators who stay honest and do not censor. And I think that's much more likely with the validator set that includes non-institutionalized at-home validators. And to your gigabit internet connection, like I highly disagree. Like in many places, you cannot easily get that. And I think a gigabit internet connection would, at least for the data scale that we are planning at Ethereum, not be sufficient to run a super full node that would download full blocks.
That's surprising. Wasn't the suggested bandwidth for ETH2 at least initially proposed to be somewhere around 1 point something megabytes per second? So it'd be like 10 megabits,
right? Sustained.
Yes,
but blocks. I mean, blocks are sent in bursts, right? Like so, unless you want to start streaming them, and you wouldn't be able to just have that as a continuous stream. You have it like once every 12 seconds. and you need to be able to like receive it from several peer-to-peer nodes as well as send it to several peer-to-peer nodes in that time span. So I think like having super full nodes is not realistic with a 1 gigabit connection. And again, I think like I cannot get one here. So like that, and that is in London. So I doubt that it's so easy to get that anywhere for $100 per month.
Fair enough. We'll move on to the last question that I have here. And this is going to be about Celestiums. So great for both of you guys. Celestiums represent a great way that Ethereum and Celestia could potentially work together. So for background, L2s can choose from a wider range of different security assumptions, whether that's a full rollup, a validium, et cetera, et cetera. And Celestiums are one such potential option where you can rely on Ethereum for settlement, and then you can rely on Celestia for data availability. So I will turn it over to John to speak to how these would work and why might they potentially be an attractive option relative to some of the other choices with Ethereum and Celestia working together in this scenario.
Sure. So I should probably start by describing the status quo around rollups and validiums, or just off-chain data availability. So the way rollups work today on Ethereum is the rollup, it's the blockchain, and it posts all its data to Ethereum. That way you can have a trust minimized light client. Unfortunately, smart contracts cannot perform data availability sampling because it requires a network connection and local randomness. That being said, I did write a proposal on ETH Research that does enable smart contracts to perform data availability sampling for remote chains, but this is very much in the research stage. But it's a possibility, let's say. But classical smart contracts can't do this. So you're left with, okay, you just have to post all your data to Ethereum, just linear cost. Not exactly ideal. That doesn't mean it's the worst solution, or it doesn't mean it's not the best solution, but rather it's not ideal, right? We would like to not have to post all that data all the time because it's linear cost. And Ethereum block space is relatively expensive now. Post dank sharding, it may be substantially cheaper, or rather it should have substantially more capacity. That doesn't necessarily mean it'll be cheaper. Depends on supply and demand. But regardless, it's fairly expensive now. This is why a variety of projects use off-chain data mechanisms. The kind of most prominent ones that people know of are validiums. So these are like ZK rollups, but that keep their data off-chain. I believe maybe ZK Sync and Starkware offer them, but don't quote me on that, or offer variations thereof. And essentially, they leverage a notion of a data availability committee. So this is a set of signers, multisig essentially, that attests to the data being available. This is obviously, well, it's better than nothing, but is it as good as we can get it? And this is where Celestiums come in. Celestiums are essentially, they leverage a technology that we call the quantum gravity bridge, which is a one-way message bridge from Celestia to Ethereum that essentially attests with the stake of the entire Celestia validator set. So it's essentially like a proof of stake bridge. It attests that some data has been posted to the Celestia, and therefore it is essentially a drop-in replacement for a data availability committee, or potentially a rollup that wants to become a Celestium. So it's a data availability service, just like a data availability committee is, and just like how Ethereum would be for a full rollup. What are the advantages of a Celestium over a vanilla data availability committee? So if a committee lies, there's no penalty. Like, I guess they lose their reputation, but like, just look at the traditional financial ecosystem for how much that reputation is really worth, right? Especially when you don't really have many alternatives. And users have no way to verify that the data availability committee is currently honest, and they have been honest in the past, which means that when they join, the only thing they really have going for them is literally just reputation that they've heard. There's no other evidence for that the committee has been behaving honestly. So can we improve on this? So these are areas where Celestiums can do better than a vanilla data availability committee, effectively with very little, if any, downsides. Since the attestation that data is available is backed by the stake of the Celestia validator set, if an attestation is incorrect, then that means at least 2/3 of the Celestia validator set has lied, which means they can be slashed through social consensus, which means they could potentially be losing an enormous sum of money. So there's a very direct and very harsh and very immediate financial penalty to the attestation being invalid that you do not get out of a data availability committee. Secondly, because the data fundamentally that is attested to through the quantum gravity bridge that Celestiums can leverage is this erasure-coded, sampleable Celestia blocks, users can actually perform data availability sampling locally on these blocks and verify for themselves that the data availability committee has not been corrupted in its history. Or sorry, not the data availability committee, the quantum gravity bridge. They can verify the quantum gravity bridge has never relayed an invalid attestation by simply performing data availability sampling on historical blocks. And they can also perform data availability sampling on current blocks as they come in locally. So at least they know that a corruption happens. Like if a corruption happens, they at least know of it. Because for a data availability committee, they can be corrupted, and users could just not know for a year. And if no one tells them, and there's a bunch of backroom dealing with stuff, they could not know forever. With the quantum gravity bridge, they can know immediately. They can even know before a relay has been before data has been relayed to Ethereum, that it's going to be a corrupted data relay in some cases. So in that context, it gives you much better security guarantees, both in the form of concrete penalties and in the form of being able to detect when corruption happens, than you get out of a data availability committee. And the downsides are effectively non-existent. I guess you could say you post data to a blockchain, so it's slightly more expensive. I mean, maybe it could be even cheaper, depending on how expensive a data availability committee wants to provide their services for. The latency, I guess, it would be slightly higher than a data availability committee, but you can get soft confirmations on the Celestia chain very quickly, and from validators on the Celestia chain very quickly. So latency is kind of it's all a wash. So the downsides are essentially non-existent, and the upsides are above security and auditability. So that's essentially Celestiums in a nutshell. So it will allow an additional option for rollups on Ethereum to have a very scalable data availability there. It's simply one option among many. There are several options, like I said before, using Ethereum itself, using a data availability committee, using a Celestium, waiting for dank sharding, right? There's many options, but this is just one option among many that rollups on Ethereum can choose to increase their throughput ultimately.
I mean, correction here, they aren't rollups if they use DACs or Celestia. But yes, I mean, so I agree that that it can be definitely an improvement for Validiums over having its own data availability committee. I guess it's going to be interesting how the pricing works out. So TBD, I guess. What I would comment on is that the additional security properties do, I think, depend on Celestia having its own independent use. Like, say it's only Celestiums, then I think it might not provide that security because there might be no one to hard fork Celestia or soft fork. Actually, hard fork, right? You need a hard fork when there's fraudulent activity. When there is a problem. So I think this additional guarantee that you get the slashing only really works if we assume that there's a vibrant ecosystem and community on Celestia, which
I'm biased, but I think that assumption will hold.
Yeah,
but I'm biased.
But I'm just saying that as an additional assumption, yes. But hopefully, yes.
Awesome. Well, I would love to listen to you guys talk all day about this kind of stuff, but I think that's a great note to end things on here for today. You crushed a lot of the questions that people like myself have had who are trying to understand the subtle differences between these designs and kind of the considerations in them, especially because, as John mentioned before, they are vastly more alike than not, especially when you look at other chains and kind of spiritually the direction that they're headed. I'm definitely going to run the recording back after we're done here once we hop off. I imagine a lot of our viewers will do the same. But just to wrap up, I'll turn it over to you guys if you have any final thoughts you have, what people might be looking out for on your projects that are coming up, or to learn more, whatever you want to say. John, if you want to go first.
Sure. So if you want to follow us, our progress on Twitter, you can follow us at Celestia.org. You can follow me personally at JAdler0. All of the Celestia development happens in the open on GitHub. All of our repos are public. All of our issue tracking is done on GitHub. So anyone can follow, anyone can contribute. We've had many external contributors so far. We currently have a testnet up. It is the first persistent, publicly accessible, literally anyone can join with no waiting or anything, I believe, that performs data availability sampling. And it came out, I want to say a month ago or something. And then, we're essentially working our way towards productionizing this network, bringing it to mainnet, along with all the other bells and whistles like Quantum Gravity Bridge and Submos. So you have your settlement layer. So if anyone wants to follow or contribute, then that's where you can do it.
Yeah, thank you. Yeah, thanks for having me here on the podcast. It's great. And yeah, I think it's definitely still a very exciting topic, and I encourage everyone to try to learn more about data availability, because it is definitely one of the most important things in order to scale blockchains. And yeah, at Ethereum as well, we still need to develop things. We still need your help. There are still interesting challenges to solve. For example, in the peer-to-peer networking, how exactly that works. So yeah, if you're interested in this, please come and talk to us, join us.
Awesome. Thanks again, guys. That's a wrap. So thanks everyone for joining. Take care.
Thanks for having us.
Thank you.
Hey, it's Tom. Our team at Delphi Media just launched a new show, NFT Collector, where two guests go head-to-head to each build a $50,000 NFT portfolio in short 10-minute episodes. They leak alpha all along the way, so click the link in the show notes and subscribe to NFT Collector on YouTube.